we have lipid-soluble ones we're going to talk about now because we're talking about lipids. We have our vitamin A. Of course, we all know that helps your eyes. Vitamin D regulates calcium and phosphorus, and there is a whole host of research into vitamin D. And we are all deficient in it in our area. Just remember, correlation is not causation. So when you have all these diseases and you also have low vitamin D, doesn't mean that the diseases are caused by the low vitamin D. So you really have to be very careful about these studies. You got to make sure that they found the link between the two. But it does, of course, regulate calcium and phosphorus metabolism. Vitamin E is an antioxidant. We're going to talk about vitamin E later on next chapter, and it is super cool. Vitamin K is blood clotting. So let's talk about each of these. Vitamin A, beta carotene, or we can call it retinol. It's lipid soluble. What color is vitamin A? Orange. What happens if you eat too much beta carotene? You turn orange. Did I tell you that I had a girl living on my floor my freshman year that all she would eat was carrots? And she turned orange. I mean, visibly orange. And we didn't have self-tanners back then. So you didn't think, oh, she went a little crazy with that self-tanner. So no, she turned orange. And that was because vitamin A is lipid soluble, so it ended up in her skin. And she turned orange. If they have too much vitamin A?
If they eat like too many carrots.
If they eat too much carrots. Oh, so it will happen in babies. All right. All right, so this is the reaction. We're going to go over it in the next slide. Again, this is an example of where I have the words for the reaction in this slide and then the reaction in the next slide. So when you're looking at this later, please just kind of look back and forth. So, so again, what we're going to do is we're going to oxidize an OH to an aldehyde. And then we're going to put that aldehyde together with the nitrogen from a lysine residue and an opsin protein in your eye. And when you have the aldehyde with the lysine, so you have the vitamin A with the protein, it's called rhodopsin. And then the photochemical reaction is taking a cis double bond and making it trans and going back and forth. And so that is, we're going to take that retinol portion, that vitamin A portion of that rhodopsin and go back and forth. And that's what the nerve impulse will be. If it's all trans, you're not going to bind to the opsin, the protein. You have to be in the cis form. All right, so let's take a look at it. Now, those of you that have had organic chemistry, what can we say about these double bonds? They are, starts with a C, conjugated. When you have double bonds, every other bond, so double bond, no double bond, double bond, no double bond, double bond, no double bond. Through resonance is actually, there's double bond character throughout this entire structure right here. And what that means is that those pi electrons zoom around the entire structure. And when you have structures like that, that means they are easily able to absorb visible or UV energy. So it can absorb photons. So that's why when you see things that, structures that are colored, you are likely to see conjugated double bonds because those zooming around electrons will absorb energy. So here you can see the conjugated double bonds. This is our beta carotene when we're munching on our carrots. And then in your liver, it's going to cleave it. It cleaves right here. And it makes an OH here. So this, your liver produces this. So this is retinol, or vitamin A. So you need your liver there in order to get vitamin A. So this is retinol. What did I say would happen next? It's going to bind to, it's going to bind to the opsin on the rod. But before it does, we have to make this OH an aldehyde. And so we have a dehydrogenase. Right? Remember, dehydrogenases do a redox reaction. So then we're going to oxidize it, the OH, to an aldehyde. It's all trans. Remember, we said that it does not, the trans won't bind to our opsin. So we have to have an isomerase that makes this one bond here a cis bond. Now that this is a cis bond, it can bind to our opsin. Our opsin is a protein on our rod cells, and here is a nitrogen, the nitrogen on that lysine residue, and we're going to form a Schiff base for you organic chemists. I'm not going to ask that. Right. Schiff base here on this. So here we still have that cis. If we do not have enough vitamin A, you can go blind. I think I had a neighbor growing up that couldn't see at night, and she had a terrible, terrible diet. So I think in that she did not have enough vitamin A. So, and again, vitamins may accumulate in fat tissue.
So the amide forms when you do isomerization of the retinol?
So the isomerization is just to make it from trans retinol, the aldehyde makes it an all to an al. The retinol, in order, you have to have it in the trans conformation in order to bind to the opsin. So this, at carbon number 11, has to be in a cis in order to bind to the opsin. Then you make the imine when you bind to the opsin. And so this is rhodopsin. And going back from cis to trans, right here, that's your nerve impulse. This is where the photochemical reaction is going to happen. Vitamin D comes from cholesterol. So what we have is cholesterol on our skin. And what we're going to do is use a photochemical reaction from the sun to convert cholesterol to vitamin D. So here we have our cholesterol. An enzyme is going to put another double bond here, and then we're going to chop. The UV chops this bond. I'm not going to ask you like the mechanism. I'm just showing you right now. So here it's chopping this one, and it's opening up. This is vitamin D3. It's vitamin D3 that is our active vitamin D. So if you go to GNC and you want to buy vitamin D, then you should instead eat eggs and go in the sun. Anyway, make sure it's D3. So then you're going to open it up in your liver and oxygen. We're going to make an alcohol here. And what else are we going to do? That's about it. Put an alcohol here, and then put another alcohol over here. And this is the active form that, that stimulates the absorption of calcium and phosphate in your intestine. So this is really what does the work. But what we need to make sure is that we have enough vitamin D3 in our diet. So you can either get it from eating an egg and going out in the sun. What has a lot of vitamin D? Is it broccoli? What has a lot of vitamin D? Spinach? Spinach has a lot of vitamin D. And then, of course, if you don't have enough vitamin D, you can have rickets or bone deformities. All right, vitamin E, also cool. We're going to see the same slide later on in another chapter. But living in an oxygen environment is not cool. It is like, I mean, it's cool because we can get a lot of energy out of it, but it is oxygen's so reactive that I'm surprised we're alive because it can cause so much damage. And what we have are two things that can take care of what we call reactive oxygen species. We have small molecules, which vitamin E is, and we have enzyme systems that can help with reactive oxygen species. I'm going to talk about those later. But vitamin E is a lipid-soluble vitamin that helps with reactive oxygen species. And what happens with reactive oxygen species or leaking electrons from the electron transport chain is what we get what we call free radicals. We've all heard free radicals are bad, but we'll talk about why. What they do is they break up membranes and cause wrinkles. So a lot of people put vitamin E on their face so that the free radicals don't get to the membranes on their face and cause wrinkles. So this L is lipid. And so what we have is this oxygen has gotten to this lipid. It's infected. It's really going to cause some bad things. And we're going to see later that this free radical can not only destroy this lipid that might be in a membrane, but then pass it on to like hundreds of other ones. So we need to like get this bullet out of there. So what they'll do is the free radical will be passed to alpha tocopherol. And the reason why it goes from the lipid to alpha tocopherol is because this free radical is actually stabilized within this ring. So it's resonance stabilized. So that's why it's more stable for it to go from the lipid to the vitamin E. Now, vitamin E is lipid soluble. So if it stays in there, then it stays in your body, right? It's not going to, you can't pass it out. So what happens is it gets passed out to a water-soluble vitamin called ascorbic acid is called vitamin C. Vitamin C, very good. So what happens is the free radical then gets passed on to vitamin C right here, and then we can pass it out in our urine. So very good. And this is where you're going to eat your green leafy vegetables. Seed oils, I guess it can be found in whole grains. So everything that we're supposed to eat is right here. So then you can get your vitamin E. Very cool. And vitamin K is required for blood clotting. Where did we see this isoprene unit before? Where did we see this isoprene unit that was repeated 10 times? CoQ10, right? Remember I said don't eat CoQ6? This is CoQ10. The 10 stood for the number of times the isoprene unit was repeated. So here's that isoprene unit again. So what did we say that the isoprene unit in CoQ10 did for coenzyme Q, or ubiquinone? It allowed it to do what? What was its function, CoQ? To go between which, are you guys okay? It went within the membrane, right? From it went within the membrane, so it had to stay hydrophobic. So it went from complex 1 and 2 to complex 3. So, and carried those hydrides. So because it stayed within there, this isoprene unit made it pretty hydrophobic. So you can imagine it doing it again here, although it's not going to be as hydrophobic because here it's only 5 carbons. So here is vitamin K1 and vitamin K2. All right, so how does it work? What is it going to do to cause blood clotting? Blood clotting comes when we chelate with calcium. And this chelating with calcium forms the clot, actually. So here, this is in prothrombin. I can't say that. Am I saying that correct? Here's the glutamic acid residue. It's going to come together with vitamin K and then chelate with calcium. And this is going to cause the clotting. You know, I'm not going to ask you really much about vitamin K other than its job is to cause blood clotting and has that isoprene unit, and the job of it is to help chelate with calcium. I'm going to briefly go over prostaglandins and leukotrienes just so you're familiar with them. They're hormone-like molecules that have been involved in many, many different processes, and it's a huge area of research. So prostaglandins, look at all the different things that it can be involved in. So what is it? It comes from arachidonic acid, which is 20 carbons. What does this 4 mean? 20 carbons. What does that 4 mean? How many double bonds it has, right? So it's 20 carbons long, and it has 4 places of double bonds. And we showed arachidonic acid, this fatty acid, in a previous slide when we were covering fats. So it comes from arachidonic acid, and we make that from linoleic acid by adding a 3-carbon unit. Now, so coming from arachidonic acid to make these prostaglandins that control or have a function in all these things can be inhibited by aspirin and also by cortisone. So if you have inflammation and you take cortisone, the way it works is by inhibiting the synthesis of prostaglandins. I know that my daughter will take a steroid when her asthma is out of control, right? And that's inflammation there.
So they make things?
Yeah, prostaglandins, it's usually like a cascade of events that causes inflammation. So you know, like if you have a problem with bleeding, you're not going to take aspirin, right? It thins your blood. But that, again, you take aspirin if you want thin blood, right? So you're not going to get a blood clot in your heart. So this is arachidonic acid, and it can make prostaglandins and leukotrienes. They have double bonds, but they are not conjugated. So just here, take a look at this. Oh, in my slide here, I don't even show this early one. So here's our linoleic acid, I guess. And then here is our, this is our linoleic acid on a phospholipid. So this is the linoleic acid on a phospholipid. We're going to take that off, hydrolyze this ester to get and make it arachidonic acid, and then we can make either our prostaglandins or leukotrienes from that. Leukotrienes are also, as we just showed, come from arachidonic acid. They're found in white blood cells, and they do have conjugated double bonds. And they're involved in our asthma attacks, and allergic reactions. They also are an area of research for rheumatoid arthritis. And if you ever hear the word echinozoids, they're 20-carbon prostaglandins and leukotrienes that are a huge area of research. So know that they come from